Hey, welcome to Mineral Talks Live, the weekly live webinar that brings you in-depth and in-person interviews with the mineral people from around the world. Mineral Talks Live is brought to you by a joint effort among the Mineralogical and Geological Museum at Harvard University, the Society of Mineral Museum Professionals, and Blue Cap Productions. Tune in every Wednesday and stay connected to your mineral world. Now, broadcasting live from beautiful Honolulu, Hawaii, the land of aloha, ukuleles, and shakas, this is Mineral Talks Live. Hello and welcome to another episode of Mineral Talks Live, the weekly mineral talk show broadcasting to you live every Wednesday. I'm Brian Swoboda, the president of Blue Cap Productions, and we really have a great show for you today. For those of you who are tuning into our program for the first time, Mineral Talks Live is a weekly webinar put on by myself representing Blue Cap Productions, Dr. Raquel Alonso Perez representing the Mineralogical and Geological Museum at Harvard University, and Dr. Eloise Gaillou representing the Society of Mineral Museum Professionals, also known as the SMMP. Now, we try to make our program as interactive as possible for you, so let me quickly describe how you can participate in every show. At the bottom of your screen, you'll see a series of buttons. There's one button labeled Chat and another labeled Q&A. Those are going to be the two main buttons that you're going to use to interact with people. Now, that chat feature allows you to type messages to everyone watching and participating in the show. When you first sign on, go ahead and fire off a chat message introducing yourself and telling us where you're tuning in from, because it's always fun to see where our friends are. Now, during the interview, our guest and I will be focused on our conversation and not really looking at the chat window. However, both Raquel and Eloise will be very active in those chats, so look for their comments along with everyone else's. At times, either Eloise or Raquel may interject during the interview with questions that you're asking, so we can get an immediate answer from our guest while they're still on the topic. Now, the second way to interact with this program is through the Q&A function. This allows you to submit general questions that we try to answer at the end of the interview. And finally, at about 40 minutes into the program, you may see a window pop up on your screen asking a bunch of questions for our weekly poll. This is just a bit of fun we like to do where you can try to predict how our guest is going to answer the 10 questions I'll ask at the end of the show. It's a bit of fun and you'll get to know our guest a little bit better. And usually when we do this, we always have a little bit of a prize. So I'm going to share with you today what our prize is, just so that you tune in to the very end. So our prize today is going to be a XRF, that's an X-ray fluorescence analysis of a mineral of your choice. So you're going to definitely want to tune into that, and let's see who can win. So now with that, let's start our program. On today's show, we're heading back to California, where our guest is broadcasting live from the Caltech campus in beautiful Pasadena. He was born in the west central region of Wisconsin and received his Bachelor of Science degree in Chemistry and Math from Wisconsin State University. From there, he went on to earn his PhD in Inorganic Chemistry at Caltech, where he ended up staying. And although he teaches mineralogy at one of the top geoscience departments in the world, he has never had an academic course in either mineralogy or geology. A contradiction? Perhaps. But then you're ready to meet Mr. George Rossman. George, how you doing today?
Hey, very good to see you and to be part of this program. Life is good here, beautiful, sunny Southern California. Glad to have you on board.
Well, thank you so much for joining. George, there's something I want to ask you, which I found was very interesting. We all know about James Dana, because he created this, his system of mineralogy that we use to kind of classify minerals. And any museum that has, a systemic system of displaying the minerals, they're using the Dana system. Now, in 2001, the Mineralogical Society of America presented their first Dana Award ever. And that was to recognize excellence from mineralogists. And you, who I don't believe you were a mineralogist at the time, you got the first award. Tell us a little bit about that.
Well, I did. Thank you. The passion of my life has always been a combination of chemistry and minerals. And when I graduated from Caltech in chemistry, during my thesis years, I was always bugging the people in the geology department to get samples of minerals to run in the machines I was using to study my chemistry compounds. So they got to know me over the years. And when time came to graduate, they called my bluff and said, would you teach a course in modern mineralogy, spectroscopy of minerals at Caltech before you take a real job? And I said, sure, I'll do that. I didn't think about it for a millisecond. And I guess they liked it because they hired me permanently. So ever since I've graduated, I've actually been in the geology department, but I've been studying the chemistry and spectroscopic property of minerals. So yes, in some ways I've always been a mineralogist, but I've ventured into relatively new directions and new quantitative studies of minerals, hopefully advancing the science beyond what most people were doing. And it's partly because of that that the Dana medal became under my possession.
That is fantastic. George, we're going to go into a little bit of detail on all those things that you talked about, but why don't we kind of rewind it a bit and tell us how you started getting involved in minerals?
Oh my gosh, that goes back to my grade school days. I grew up in west central Wisconsin, where it was mostly sandstone and some limestone. But occasionally I would find little teeny crystals of either calcite or quartz, which fascinated me. And over time, I let it be known to my friends that I had these, and some of my friends that were in Illinois started giving me little fluorite cubes from the Rose Clare area in Illinois. And that got me further enamored with minerals. Then a major thing happened. The daughter of my next door neighbor took chemistry at the local university in my hometown. And I guess she didn't like it because as soon as she quit the course, she gave me her chemistry books, which I found fascinating.
Oh
And particularly one of the books called The Lang's Handbook of Chemistry had a list of minerals and the chemical formula of minerals in that book. And I began to become aware that we had all sorts of different elements. So I became interested in elements. And I started to collect things. Well, like here's a rod of zirconium metal, and here's a rod of titanium metal, and here's a sheet of niobium metal. But as Celine said last time, all of these metals look the same. They're gray metals. You can't get excited about them. So I found the color of the minerals more interesting. I was collecting agates on the very shores of the rivers in Wisconsin near where I lived. And I decided one day to polish one of my agates, Lake Superior agates brought in by the glaciers from the basalt flows up in basically Minnesota, Canada. And to do that, I had to get some polishing compounds. So I ordered by mail from a company in Pasadena, California called Grieger's. And I ordered a supply of polishing powder and grinding powder. And when it came, because my order was over $25, big money back in the 60s, they gave me a free bonus. And the bonus was this little crystal of tourmaline. And I'm going to put it on a light stand here so you can see it. And I'm going to reverse the camera here. So now we're looking at my very first tourmaline crystal. And the thing that amazed me, this young kid in grade school, here we had what I thought was a rock at the time. It was transparent like a piece of glass and came in multiple colors. I'd never seen anything like that before. And that just absolutely fascinated me. So I took it in and I showed it to my teacher. Oops, wrong way. I showed the sample to my teacher and I asked my teacher to explain how can it be that this rock I had was transparent and came in multiple colors. And teacher didn't have a clue about this. And that really got my curiosity going about where the color came from. So combining my interest in chemistry, which I've already started to develop, with my interest in minerals, I became absolutely fascinated with the chemical origin of color in minerals. And I set out to study, again, back in grade school and high school, I studied color in minerals and the chemistry that you needed to do to analyze these minerals to determine what chemical elements are in them to give rise to color. So it's literally this little piece of tourmaline right here that really started my career in science and mineralogy.
I absolutely love that the catalyst for starting you down that road is a piece that you still have and you know exactly where it is.
Oh yes, I love this little piece. It's my 23rd sample in my private personal mineral collection as a kid. And to this day, I still am very thankful that I got that, is this free bonus from Grieger's here in Pasadena, California.
Now, George, do you have your own collection?
I as a professional, decided I would not seriously collect minerals. I did not want there to be any confusion between what I was getting for research versus what I was trying to get for personal enjoyment or personal sale. So yeah, when I go to a mine, for example, around the world, I'll collect a little souvenir out of the dump, but nothing really special. But no, I do not seriously collect minerals as a professional mineralogist. My gosh, I got 18,000 beautiful samples here at Caltech to play with, so I really don't feel compelled to have my own.
Fantastic. Now, you are in your office there at on the third floor, correct?
That is correct.
Can you show us a little bit around the office and tell us what we're looking at as you're showing?
Sure, I can do that. Let me reverse the camera here.
Ow. I'm just kidding.
Ouch. So if we start over by the door, I have a series of cabinets that contain mineral specimens for research. Let me just open one. For example, here's one on quartz. Well, what we have here are, in this particular drawer, synthetic quartz crystals. These crystals are from Russia, Cernigolovka. Here are crystals from Bell Labs for telecommunications. Here's a beautiful crystal of synthetic ametrine made in Russia. And it's literally hundreds and hundreds and hundreds, thousands of specimens I have in these drawers. Drawers full of tourmaline samples. Some I got from the Himalaya mine, thanks to Bill Larson, with whom I became good friends many, many years ago. Some from various other places around North America. Drawers full of tourmalines from other localities around the world. Various companies like Pete Flusher at Overland Gems in Pasadena would give me samples that were not saleable, broken, cracked, included pieces they could not make into gems. But these became the feedstock of doing research. Or perhaps this one, a beautiful Paraíba tourmaline in matrix, beautiful blue copper-containing tourmaline in the matrix from Brazil. So I've put together an enormous collection of things like this, drawers full of different minerals, drawers full of example of barrels. Let me just show you one here. Here's one of my boxes of barrels. And what we have here are beautiful blue barrels from the Ukraine. They've been heat treated, and here are the way they come out of the ground, the yellow crystals. And I'm interested in studying what is going on. Why do they turn from yellow to blue upon heat treatment? What are the atomistic causes of this change? What chemical elements are involved in them? Another thing I get involved with, and I have in these drawers, are I help to characterize new minerals. For example, in this little box right here, I have samples of pizotoite. And some of these are the samples that we use to characterize pizotoite as a new mineral. Okay. We did the spectroscopic studies at Caltech. Other people did the crystallographic studies. But again, all of us stand on the shoulders of many other people. Mineralogy is a collaborative activity, and no one person does it all, but by getting good colleagues, and in my case, profoundly good students, we're able to do a lot of things involving drawers and drawers of samples. Like here are some corundum crystals, for example. These are from India, and various little vials and bottles, all of these boxes full of crystals that I have, often from various dealers around the world, various collectors, or sometimes involving collaborations with people in the various publications, Gems and Gemology, Gem A, who get together with their writers and get me samples I can send for research. Then I got boxes and boxes of samples up here, which are part of our studies. So for example, one of the big controversies in past times was the concern about red Anderson Feldspar from China. And this stone came out as the official stone of the Beijing Olympics. The question was, are these red stones natural as they were being sold, or were they treated as rumors developed? And Jewelry Television went out and they had one of their people called Jewel Hunter Jack find where the source of the feldspar was coming from, and it turned out to be Inner Mongolia. And these are the actual Andesine feldspars that were being mined from the deposit in China. And these were being treated in the laboratory by diffusion to ultimately turn them into the beautiful red gemstones of commerce. So
No
I get
kidding.
involved in doing things like that, compliments of both the industry, the television networks, and various people that are doing studies of this sort of type. Oh yeah, I do happen to like tourmaline, so I got a lot of pictures here of tourmaline in my lab. Tourmaline is certainly one of my favorite minerals. And here are some micas I got. I was a very good friend of Rock Courier of Jewel Tunnel Imports.
Sure.
He and I go back way back when. I brought to him his first large sale of his career, and that made us good friends. And then just more cabinets full of samples. These are andesine samples from various places around the world. Here we have the Manicara, the beautiful stone known as Manicara, which is the amethyst grape deposits from Indonesia.
Yeah, the great chalcedony, as they've been calling it in the field.
And I helped characterize that with some of the people mining it. Here are some samples, well, from the rough database. All of the infrared data on the rough database is out of my lab and some of the Raman samples. But again, it's just drawers and drawers and drawers of samples, and it's file cabinets full of various chart paper that represents data collected in the old days before everything was digital. A few souvenirs from my research. We did research on the chemistry of dendrites. And this is one of my favorite dendrites right here. It's from Afton Canyon up here in California. Just various mementos, some manganese +3 in the mineral piemontite, a beautiful piece of Azurite Feldspar on orthoclase from one of the mines in the Pala district. I visited the Amazonite localities in Colorado. That's a little souvenir I got back. Here is one of the fluorescent rubies from Los Angeles.
Yeah, look at that.
Very nice sample. I like that one a lot. And pegmatite, this is part of the Himalaya pegmatite dike, some of the quartz crystals coming out. So it's a variety of things like that that I work on and have tried to attain for various collections. Lots and lots of folders containing partially completed manuscripts and a lot of journals, American mineralogist journals, which nowadays with everything online, quite frankly, I don't read the paper anymore. Everything I do is online. So that's
you're like the mad scientist who everyone wants your lab.
Well, in fact, in my laboratories, which we will visit later, I have roughly 80 people a year using the lab facilities to characterize minerals, materials, electronic devices, filters for astronomy, chemical compounds. Yeah, I'm very much a hands-on person, as you might guess.
Wow. Now, what kind of equipment do you have there at Caltech to run these analysis?
Well, maybe it'd be better if we just walk next door and I'll give you a tour and show you some of the machines.
All right,
So
take us with you.
Take a look, and we will go and see what we have. Let me get back here till I rotate. I'm going out the door. That's my office number. Into the hall of the building. Oh, I can't pass this up. This is one of my favorite pictures of tourmaline. It's a beautiful tourmaline from Italy. The black cap on the top is the mineral phoitite.
Phoitite, okay.
The crackly stuff at the bottom is elbaite from Elba, Italy. But the beautiful, clear, transparent material I'm looking at now is the mineral
Rossmanite. Named after, obviously, you.
That is correct. In our hall, we have pictures of minerals named after people that were at Caltech. This is Johnsite, named after our former professor, Dick Johns at Caltech, who was very important in studying the pegmatites of Southern California.
Speaking of Dick Johns, I've just put up a photograph from one of the mine bashes held down in Pala, and that is you on the far right with the glasses standing right next to Mr. Dick Johns. Good friend to everyone down in the Pala region, really good friend of my father's, and very helpful in a lot of the work that was going on down there at the Queen Mine.
Tremendous. I remember that well. Bill Larson was incredibly helpful to us by letting us come into the mines, letting us collect samples and bring students to do research. And now we're going to enter one of my laboratories, the Mineral Spectroscopy Lab.
Do we have to do the evil chuckle?
Oh, ho, ho. No, we don't. So this is a room full of analytical equipment, one of several that we have here. Let me just give you a very brief tour. This is an optical microscope hooked up to an optical spectrometer for quantitatively determining the origin of color in minerals. Here we have a Lib spectrometer, one of the instruments they currently have on Mars to determine the chemistry of Martian rocks. Coming around to the other side of the room, we have a spectrometer system over here, which we use to study fluorescence in minerals. Then over in the corner, we have an X-ray fluorescence machine that I'll be very happy to demonstrate how we quickly determine the chemistry of a mineral. We have another device for determining the ultraviolet spectroscopy of minerals. And then two of our major facilities, let me come over here. Here we have a Raman spectrometer, which is used for phase identification. And we have in the other corner, a second Raman spectrometer, which is also a very important mineral identification tool where one can analyze samples on the order of 1 micrometer in size. And again, if we have time, I can demonstrate how that works. Also in the laboratory, we have a tool for crystal orientation. It's a crystal orientation device built in part by Tim Thomas, who used to work at GIA, another organization with which I've had very good rapport over the years. And this allows us to determine where, for example, the C-axis is on a crystal, so we can do orientation studies when we do all of the optical measurements. This is only one of multiple labs I have, but this is the one with the greatest number of pieces of equipment in it. Anything in particular you'd like to see?
Well, George, I think you've got all these different machines, and it might help our audience if you can show us how a couple of them work and explain why that machine is important and the benefits that it provides to not only Caltech, but the mineral world.
Okay, we're going to come over here in this corner, and we're going to turn the computer on. And this is a machine known as X-ray fluorescence. And I have a sample here.
If you allow me to interject, that is the machine that you will use to identify the winner of today's contest, the sample that they submit. Okay.
That's certainly, I may use other machines if necessary, but this will be a primary one.
Okay.
Now, here on the desk, I'm holding a sample. It's a black mineral, and I want to find out what this is. It's kind of hard sometimes when you get black minerals to look at them and determine exactly what they are. So I'm going to put this machine to work. I'm opening the drawer. Inside, we have an X-ray source over here, a little teeny opening that shoots X-rays up. The sample goes on top of a plastic film, and there's an X-ray detector right here that detects the X-rays given off by the sample. Sample's going to go in, place it on the machine right here. So now the sample is placed over the X-ray source. Load it up a little bit. Oh, okay. And close the door. Now I'm going to come over to the machine, and I'm going to tell the machine we're going to start. The first thing the machine does is it turns the voltage on the X-ray source up to 45,000 volts. It's found an optimal current, and now we're building up an X-ray spectrum. We're looking at the intensity of the X-rays coming out of the sample. We put in high energy X-rays that knocks electrons out of inner orbitals. The electrons come down to fill the vacancy, and they lose energy in the process, emitting soft X-rays. Now we're going to 15,000 volts. And now we're looking at the light elements in the sample. And again, we can see some peaks from the light elements. So in roughly 15 more seconds, this analysis will be done. We'll be able to process it, and we'll be able to see exactly what composition is inside the sample. Here we go, countdown 1, 0, and now we're going to go to the machine. We're going to process the results. And rather than saving them, I'm simply going to process them directly. Now the computer goes to work, it identifies all the peaks, and it comes up with a list of chemical elements that it's found inside the sample. Well, let's take a look at this one right here. This is elements rather than oxides. We can see that there's major silicon, there's major zirconium, there's a little bit of aluminum, a little bit of hafnium, trace of iron, some yttrium, some bismuth, and a moderate amount of uranium. This is almost certainly a zircon, zirconium silicate, that has uranium in it that makes it naturally radioactive, and a few other minor chemical components. Wow. Bingo, in less than 2 minutes, I've identified what the sample is.
That was fast.
So again, we can come in, take my sample out. Now I can put it in a box, I can label it, as I know what this critter is.
Now, how does that differ from a machine like the Raman machine?
Well, Raman works on a very different principle. X-ray fluorescence works by ejecting X-rays from a sample. Raman deals with vibration. I have a box of material here from Hihoshi in Madagascar, and it's a blue material. It comes from very near the sapphire fields, and I have one little sample in a box. We're going to put it in the Raman machine. We're going to identify what this sample is. So I'm going to come over here, and I probably am going to have to set this up in a tripod so I can use both of my hands.
Look at how prepared you are.
Okay, well, sometimes we are and sometimes we aren't.
I spoke too soon.
So I'm now aiming at the machine. I'm going to open up the main compartment to the instrument. And before we started the broadcast today, I put a piece of silicon inside the machine, which is a calibration standard to make sure everything was working perfectly.
Okay.
I'm going to take the silicon out and I'm going to open up with my teeth the little box of blue material. So here's the blue sample coming in, and it's going to go underneath the microscope lens right there.
Okay.
Now I'm going to focus into the microscope. I'm going to look down and make sure that the sample is in focus, which I just did. And you can see on the video screen what I'm looking at right here. Now I have it at a 50x magnification lens.
Okay.
And what I'm going to do next is I'm going to turn a laser on so we can put a laser on the sample. And you will soon see, oh, door wasn't closed. Soon see a laser spot appear on the screen.
Sure. Okay, the green spot.
A little spot in the center here, which I'm focusing and defocusing.
Okay.
So that is the spot we're going to analyze. I'll move to a clean area without any cracks. So there's my laser. I'll make the laser a little bit brighter so you can see it more easily. There's the laser spot again.
Wow. Okay.
So now we have a laser illuminating our sample. We're going to tell the machine to shine the laser on the sample and look at the different wavelengths of light coming out of the sample. The vast majority of the light coming out of the sample is going to be the wavelength of the laser that's coming in. But some of the laser is going to interact with the sample and is going to add or subtract vibrational energy from the sample, and it will shift the emission of the light coming off the sample. And it is the shifted wavelengths that are going to be the important measurement that we call the Raman spectrum. So my machine is now starting to scan. It's aligning the optics. It's recalibrating the system. And now just in a few seconds, the actual scan will start. It takes 10 seconds for the first wavelength to go across the detector. So we have to wait 10 seconds to see the first result. And here we see the result coming in right now. The red trace on the screen? Oh, a big bump. That's a peak. We see a number of little weaker peaks on the screen. This is the Raman spectrum. I'm going to do a baseline correction to straighten out everything. And at the bottom is my corrected baseline. I'm going to accept that. And I have a position marker of where the different peaks are in the spectrum. Now we have to take this pattern and compare it to a library. So I'll do something called a library search. Find it here. Here we go. Library search. And now the library is searching, and it says it's fluoroapatite.
Fluoroapatite.
And all of the different answers are apatite. So clearly the blue sample I had from Madagascar is an apatite. In less than a minute and a half, I've identified it by the Raman method. And here
I know John Rackavan is jumping up and down. He's like, yeah, another apatite. But I mean,
oh, of course we did apatite. We had to do that for John. So this is the nature of what we do routinely. I'm using the rough database, the big database that Bob Downs put together at Arizona. And with this database inside our computer, plus our own other databases that we have a tremendous resource to be able to identify minerals with this technique called Raman spectroscopy.
It's like a fingerprint machine.
And for $250,000, you can have one too.
But I heard I could get that as an app on my iPhone.
Oh yeah, I mean, the price is coming down. This is a laboratory grade system with very high resolution, but lower resolution systems that are quite useful still can come down very much in price. And I'm sure in the future, they're going to be surprisingly widely available.
Now, they wouldn't have anything like that that would be field ready so that you could take that in the field, would they?
Oh, yes, you can. There are field portable Raman. There's field portable X-ray fluorescence.
Wow.
They don't have the resolution of these expensive laboratory machines, but they're perfectly adequate to say if you have zirconium, for example, in the field, if you have rare earth elements, or for portable Raman, you can actually identify whether it's feldspar, quartz, or beryl, or something like that. Yes.
Wow. Now, George, do we have time to look at one more machine that you might have there?
Oh, we sure do. What I think I'll do is go next door and show you an infrared machine, which is another major tool that we use. I'm going to walk out of my lab, turn the corner, and put you back on view. Now I'm going to go down the hall, and I'm going to go into a second laboratory, which is the infrared facility. So in this room, we have two infrared spectrophotometers. These are devices that measure the absorption and reflection of infrared wavelengths on and off of samples. We can also run it through a microscope, so we can do very small areas, a few tens of micrometers. And then we have another machine, which I'm going to demonstrate, called an Attenuated Total Reflection, ATR, a very, very powerful method for identifying minerals in the infrared portion of the spectrum. So let me show you what we're going to do with this. I'm firing up the machine. Okay, the machine is now on and running. And for an unknown sample on the desk, I have this piece of black material. It's kind of hard for you to, well, go ahead, Brian, what is it? You're not going to be able to tell looking at it.
No, it's a rock.
It's a rock. Actually, it's a single mineral.
It's
so what I'm going to do
it's an amphibole, George.
Say again?
An amphibole.
Okay, we have one vote for amphibole. Amphiboles are black. So I take my diamond saw and I saw off a little bit of powder, which I put on this piece of paper. You can see the pile of powder here near my finger. And I'm going to go over to the machine. And we're going to look here. And if I turn the instrument on, you see a little bit of orange light coming out of the center.
Yeah.
That is a diamond. And the diamond is the holder for the sample. So I'm going to put a little bit of the powder on the diamond. Excuse me here while I try to steady my hand to do this. I need good coordination to handle these small amounts of material. There we go. A little bit of glare from the light, unfortunately. Okay, there we go. So now I'm going to take a small little shovel. I'm going to take some of the powder off my pile of powder. I need less than 1 milligram to do this. And I'll put the powder, spilled it, on the diamond plate right here, like that. Now my diamond is covered with powder.
Okay, so you've covered the orange in the powder.
Right. The orange was laser light, or the orange was a light source, actually a laser light, coming through the diamond so I can see.
Okay, gotcha.
Now I'm going to take a rod and I'm going to squeeze down on top of the powder to put it into intimate contact with the diamond.
Okay.
We're going to shine infrared light into the diamond and bounce the infrared light off the top of the diamond back to my detector. But some of the light is going to sneak out of the diamond and interact with the sample of the mineral on the surface of the diamond. And it's going to attenuate the amount of light that would normally come through. That's what we call this attenuated total reflection. And the light that is absorbed will be infrared wavelengths that are a fingerprint characteristic of this particular mineral, amphibole, Raquel thinks it might be. So I come to the computer and I'm going to now go over to the thing that says collect sample. So now the machine is starting up. I'll give it a no-nonsense name. And the machine is aligning. It's turning the gain on automatically to get the optimum signal. And now we have a pattern appearing on the screen. I can tell already that this bump area down here on the screen is hydroxide ions, OH. This is a hydroxylated material. I can tell from the other end of the screen up here that this is a silicate. If you do this enough, you gain familiarity. So I'm going to say yes. I'm going to save this. Now I'm going to go to a search routine. Oh, let's see. I'm going to go to a search routine where I can search through a library and find out what it is. And the answer is, number one answer, a beautiful match, is lizardite, one of the serpentine minerals. My sample came from Norway, but lizardite is lizardite. So in just a matter of a few seconds, I've identified this black hunk of rock, not as an amphibole, but rather is the serpentine mineral lizardite.
Fantastic. Wow.
It's very, 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 very helpful to have this capability, of course. We use it to identify phases. We also can use it quantitatively. One of the big things that we have done in the past is we've used the infrared spectroscopy to determine what water content is in various minerals. One of the questions that my students and I have asked over the years is, where is the greatest repository of water in planet Earth? You'd say the oceans. The oceans are deep. They're 5-6 kilometers deep. They cover a major fraction of the Earth. But if we take a look at the rocks deep down inside the Earth, the volume of rock in the Earth is enormous compared to the volume of the oceans. And we've taken rocks that come out of diamond pipes, for example, kimberlites, that bring minerals from very deep in the Earth, garnets, pyroxenes, olivines, and other minerals. And we've measured the hydrogen content of bound water inside these spaces. And we find, lo and behold, that there is probably more water tied up in the rocks in just the mantle of the planet than there is in all of the oceans and atmospheres and biology of the entire planet.
You know, George, I know you mentioned that to us yesterday when we were doing our run through, and my mind just kind of exploded, and it was so hard to fathom. But after you explained the depth of the rocks, it makes a lot of sense, and it's incredible.
Yeah, it's something that really has been a major advance in science, being able to quantify the importance of this global reservoir of hydrogen tied up in minerals that we nominally consider to be anhydrous.
Now, George, maybe you could take us back to your office and show us some of the benefits and the applications that we as a society gain from the research that you're doing. And then we're going to run downstairs and take a look at your little mineral museum.
Okay. leaving the office, or leaving the lab back now into the office. One of the things that we got to remember is that mineralogy, way back when, was the start of chemistry. The alchemists were trying to turn various things out of the ground into gold and whatnot. So mineralogy is the basis of chemistry. Also, mineralogy is the basis of a lot of our material world today. Early on, for example, rubies were used to make ruby lasers. This is a rod for a ruby laser. And it's a synthetic ruby, obviously, but it was by the study of natural rubies that the idea came about to make some of the very first solid-state lasers. Other lasers are made out of a synthetic garnet, a yttrium aluminum oxide YAG garnet. And these are boules of synthetic garnet doped with neodymium, which are the basis of very powerful solid-state lasers. And again, this type of study came up from minerals. We studied minerals to understand structure and chemistry. Then the material people are able to convert it into technological useful materials. Another one, let's see if I have, yeah, here's another one. Here is yttrium iron garnet, sometimes called YIG, Y-I-G. This material is important in microwave telecommunications as a frequency filter. Again, it's a synthetic material made in the laboratory, but the idea for it came out of the study of natural minerals. Another thing that's very important is the hottest solid state laser today is titanium doped sapphire. This is sapphire with titanium +3 in it. It's a boule made synthetically by Union Carbide Corporation. But this is the basis of tunable laser technology. There's a little hole drilled out of it here. You can see that maybe the mark going through. It was a rod that was drilled out to make a very important laser used in science and technology. So our world is full of things, lasers, forsterite laser, alexandrite laser, garnet lasers, for example, all of which come from initially studying geological materials. Another important area, of course, is synthetic gemstones. Gemstones are minerals. I do a lot of work with gems because I study color, and certainly color in gems is important. I've had good rapport with the gem industry. I've had people in the gem industry give me samples of gemstones to work for science. And again, we got to remember that gems have been a major motivation for studying minerals. And again, there are a lot of synthetic minerals. Diamonds, for example, synthetic ruby, synthetic emerald, all come out of the technology that originally developed on minerals. Oh, and hey. Let's not forget quartz. Oh my gosh. I'm holding a cell phone. You're looking at computers. All of these devices have quartz crystals inside them, which are the timekeepers. Again, the quartz in technology is synthetic quartz, not natural quartz. But the whole idea for all of these things came out originally of the study of minerals.
Fantastic. Well, George, maybe you can start walking downstairs. I'd love to take a look. I'd love to share with everybody the mineral collection that you have. While you're doing that, Raquel, why don't we go ahead and launch the poll? We're a little bit past the 40-minute mark, but I think that's okay. And George, you could go ahead and talk to us about maybe some of your influencers and people who have helped you out getting where you are.
Well, clearly I've had a very good rapport early on with Rock Courier of Jewel Tunnel Imports and Bill Larson of Pala International. We hit it off very well in the early days, and both of them have been very, very important to me. People in the industry like Mike Gray, Rob Levinsky, James Zygrass, all of these people have been important to me and contributed. Major companies like Nancy B. Incorporated would give the gemstones that were damaged, and then rather than trying to recut them and reset them, they would simply donate them to Caltech for research. Very, very high quality materials for our research purposes. So it's been numerous people over the years, commercial people, collectors, and companies, all of which have been important. And I got to give really special credit to Mike Scott, the guy that put together the rock and stone collection. He was a Caltech graduate, and he's been a very, very important source of support for samples and other activities that I've been doing. So enormous thanks to this person for what he has been up to.
Well, I'm going to give Mike Scott another shout out and thanks because I know that he gifted you the iPhone that you're using to broadcast the show. So thank you, Mike Scott, for that.
Okay. Very
All
good.
right, let's look at some of your great specimens on display here.
Okay. I can't see the video yet, but I'm gonna, oh, there we go. So I'm in a museum room that we have now where some of our most valuable and most beautiful materials are being stored. This is a high security area that we have that represents materials that we've researched, materials that have been donated to us as part of our way of encouraging people to become enthused about minerals. Let me start with California. In the wall in the back, we have a lot of materials from California. Oh, for example, here is a collection of faceted benitoites from the benitoite locality in California. This is one of the largest.
Great gemstone.
Yes. And then, of course, here is the benitoite in its host environment inside the rock. It occurs with the mineral neptunite. So we have the state gemstone of California, benitoite. We have the state mineral of California, gold. And we have the state rock of California, serpentine, or serpentinite rather, made up of the mineral serpentine.
California is well represented.
Oh, yes. Now, how can we not talk about California without mentioning tourmaline? Tourmaline
Yes.
from the Pala district or the Himalaya district. These are some of the samples that we've obtained over the years of beautiful tourmalines. We got these from Tommy Warner, that was part of the foundation of Riegers back in the pre-1960 period. Beautiful examples of tourmaline. We have examples of faceted tourmalines in the little display case right here. Many different colors. All of these are from San Diego County, primarily from the Pala district and the Himalaya mine district. And let's see, we have, oh, how about this little teeny barrel of morganite from Mesa Grande in San Diego County.
Oh, that's one of the smaller ones.
That's one of the smaller ones, what can I say? We have another one from Harriet Hill in Pala. Let's give you a little size right
Yeah.
here. Nice hexagonal piece. And let's see, also from the Pala district, we have this morganite, probably from the White Queen area. You can see the beautiful clear interior inside of it. Then we have a number of gemstones from America. For example, over in the corner here, we have pyrope garnets from the Carolinas, North Carolina, and we have Idaho almandine garnets. Here we have pyrope garnets from the Arizona and the Mexico border area. And then we have some San Diego, let's get the glare here, San Diego spessartine garnets right there. Okay, oops, there we go. Make a little larger. And then just more tourmaline. Here we have Maine tourmaline, for example, the blue, beautiful blues and bluish greens from Maine. Cut spodumene from San Diego. And here's some little spodumene crystals we have on display.
And those are from Pala.
This is from the Pala Chief Mine.
Okay.
And here's another one, a bigger one, again, from the Pala Chief Mine. And then a smaller, a very small one from the Pala Chief Mine.
And that is currently being operated by our friend Jeff Swanger. So we hope to always see more of those.
Right. Oh, of course, we have San Carlos for peridot. And then we have faceted peridots, again, from the Arizona and New Mexico region. Clearly, anybody with the name of Swoboda ought to recognize this. It's from the Stewart lithium mine. And here we have some fine blue sapphires in the back from Montana and pink sapphires from the Carolinas in the front. And some fancy color sapphires, again, from Montana. So this is.
So those are yogos in the far back, correct?
Those are yogos in the far back. That is correct.
Yeah. Classic cornflower blue. Beautiful.
Yep, love them. And then we got a few international ones for comparison. Here's one of the ones from the Kilimanjaro region in Tanzania, showing what it looks like in ruby within the zoisite matrix. And again, just some other tourmalines along the way and some Mexican garnets. But let's come over here to the other side. Here is a case that is primarily copper minerals. We have a number of copper minerals from northern Michigan. And one in particular is particularly interesting. One coming up is the one that was featured in the Mineralogical Record, California Collections. And there it is right there, crystals of copper. Here we have more copper and big calcite crystals from the Michigan area.
Wow.
How about a copper skull from the Michigan area?
Oh, that's great. That's a great one.
And again, we have copper crystals from Calumet area in Michigan, Keweenaw Peninsula, copper and calcite. And here's an Azurite Rose from Bisbee, Arizona. Very pretty little rose. And more copper and calcite, and then some very, very large Spanglite crystals. Oops, gonna get this larger. Nope, I can't make it larger. Spanglite crystals from Bisbee, Arizona. Almost, they're basically as large as the ones that Celine showed last week. And some copper oxide cuprite, the fibrous variety. So just various beautiful copper materials we have here for people to look at. And I'm coming up on some, here's some beautiful azurite malachite. Everybody, of course, loves azurite and malachite. Nice samples that we have on display.
Nice.
And some, here's orichalcite. Beautiful material. Here's a huge linerite crystal right there.
I can feel everybody collectively leaning into their screen. That is enormous linerite.
Yes, it may be the biggest one in the world, possibly. And then let me come down to one of the lower cases and tell you a little bit of story. One of our former curators, by the name of Jack Rodecore, went to the Kelly region near Socorro, New Mexico, and he walked up to the mine and he asked the bulldozer operator, where in the mine can I find smithsonite? And the bulldozer operator said, well, just follow me. He drove the dozer over and he basically picked this up and gave it to Jack Rodecore. That's a huge piece of copper containing blue colored smithsonite.
I've never seen a bigger Kelly smithsonite ever.
Yeah. I got to tell you one story. I got to do some science here. We all like pink tourmaline, but one of the things that we did, in part thanks to Bill Larson, that let us take students into the mine and collect samples and measure properties inside the gem pockets. These tourmalines did not grow pink when they first grew in the pegmatite. At the temperatures at which they grow, 500 degrees, 600 degrees Celsius, they are almost completely colorless. If I put them in a furnace and heat them to 500 degrees, within 20 minutes, half an hour, the color goes away. But if they're exposed to ionizing radiation, gamma rays, which come from the decay of potassium in potassium feldspar, a major component in the mines, they could slowly have gamma rays passing through them, striking the manganese ions that start out in the 2+ oxidation state. An electron gets stripped away by the force of that gamma ray, and the manganese becomes manganese 3+, which is intensely pink. These pink tourmalines, in fact, almost all pink tourmalines, are a product of natural radiation, not a product of the way they grow in the mine. In the other corner, we have international minerals of various types.
George, let me ask you a question on that. So do they grow clear and then become irradiated, or are they being irradiated and being colored as they're growing?
Well, the work of Dave London in Oklahoma suggests that these things grow very rapidly, just a matter of hours to days. But they're in California, sitting in the pegmatites for about 92 million years, slowly accumulating the very feeble background radiation.
So then they
So
are growing, it sounds like they're growing clear, colorless, and then after the growth phase, they're sitting there and being irradiated by the surrounding feldspar and then changing color.
That is correct. They become pinker and pinker with time. And now commercially, people are exposing them to additional radiation from gamma rays or electron beams to make them even darker. Now,
okay, so in the case of like a Pala blue cap tourmaline, and I know you've done some studies on that. What if it's being irradiated and changing color because of the exposure to the gamma radiation? What is going on with the termination that gives it a different color?
Okay, the iron compound in the tourmaline, for example, like the main tourmalines here, the iron is relatively inert to gamma radiation. It doesn't really do much of a change. So the iron pretty much stays the way it was when it was first incorporated, where the manganese undergoes this radiation-induced change. If the iron is in the reduced state, iron +2, the tourmalines will be blue. If you have a mixture of oxidation states, then they ultimately become these black tourmalines, which are so common in the schorl and the foytite and these other tourmalines that we find. If we have titanium and iron in the tourmaline at the same time, then we get the greens. So pure iron is blue, iron plus titanium is green, and mixed oxidation states of iron typically is black.
Okay, so these are all being incorporated into the crystal as it's growing, and then the radiation brings the color out.
That is correct.
Okay, great.
Or nowadays, it's done in a lab all over the world. Okay.
Fantastic. There was one other thing you were going to show us before I interrupted. Sorry.
Oh, okay. We're looking at the international minerals. For example, here's a great big piece of nepheline from Mogok, Myanmar. Here's some vanadinite. This one is from Chihuahua, Mexico. And it's just a variety of different minerals. Pyrite, for example, some interesting calcite, nice gypsum rose right here. A little teeny pyroxene and azurine right here. Well, what can I say? There's the clinoenstatite right here. We have not only sort of the favorite collector minerals, but also the minerals that make up the planet. Oh, let's see. Here's kind of some cute calcites from La Potosi, Mexico. And one of the ones that really attracts the European collectors is this Fosgenite from Sardinia. That one turns out to be very popular with the Europeans that come through because of the size and the clarity.
Wow.
I kind of like the titanite here, the beautiful green color of the titanite. It's chromium primarily that gives rise to the color, as opposed to the black titanite. These are some borates I collected from the Thompson mine in Death Valley, a private mining enclave within Death Valley itself that had some fantastic Colemanite crystals coming out some years ago. Oh, I know this little barites, for example. There's another barite. Oh, smithsonite. There's smithsonite from Inyo County, California, the Cerro Gordo mine up at the south end of the Owens Valley. It's kind of a nice one.
Wow.
Yeah, wow. Now, one of the things we did at Caltech is we determined the first accurate age of planet Earth. Claire Patterson was the professor that did that. And he used the meteor crater, the Canyon Diablo meteorite, to get some of the iron sulfide, troilite out of it that was used in the age dating. So again, we're very much into meteorites here at Caltech. We've discovered, like 40 new minerals or so in meteorites, many of them primordial condensates from the solar system. My colleague and former postdoc, Chi Ma, that now runs our analytical facility, has made it one of his passions in life to examine meteorites and find microscopic new minerals that represent primordial condensation at the very beginning of the solid materials of our solar system. Here's a little teeny tektite.
Itty bitty one.
Yeah. Oh, let's see. Here's some nice hematite from Cumberland, England. In borates, California is borate country. Here's a nice cluster of Colemanite crystals from Boron, California. One of my favorites is the selenite from Mexico, Chihuahua, Mexico. Kind of like that one. And a little bit of gypsum crystals from Nicaea. One of the favorites for the kids we have on display are dinosaur eggs. And the most favorite mineral of all for young kids to look at is not this mica, but the salt crystal. The parents say, hey, this is where salt comes from. And the kids go wild when they suddenly realize that salt is a natural mineral. And my gosh, it can look like this out of the ground.
Good thing you have that behind glass. Otherwise, you'd got a lot of kids licking that.
Yeah, bulletproof glass, a lot of security here.
Good.
So this is kind of the idea of what we have in our collection in the museum area here. It's open to the public when it's not being used for meetings during daylight hours. Well, of course, now Caltech is closed due to COVID, but normally it would be open to the public. And it's a small fraction of our 18,000 research minerals, primarily the ones that are so beautiful, we got to display them or need all the added security we have in the room.
Absolutely, and that's well appreciated, showing the respect for the pieces that have been donated to you. George, we are at the 1 hour mark, so we're going a little bit over time. So I'm going to cut to the 10 questions right now, and we'll go through this, and then maybe at the end, if you can hang around a little bit, we'll do some Q&As.
Glad to do so.
Thank you. Okay, so these are the 10 questions that everyone watching has been, they've been polled about, and they've already provided their answers. So now we're going to get the answers from you. So 10 questions, rapid fire, without really thinking. You got to respond which one you have a preference towards. Number 1, agates or tourmaline?
Tourmaline.
Tourmaline. Number 2, food preference, surf or turf?
Fish.
Fish, that would be surf. Okay, this is a tough one. Singing or dancing?
Singing.
Singing.
I like to listen
Android
to it,
or I'm sorry, what was that?
I prefer to listen to it, not to do it.
Okay. Well, maybe we'll get you to sing sometime. Question number 4, Android or iPhone?
iPhone is what I use.
People who are paying attention should have the answer to that. Number 5, vegetables or fruits?
Fruit. I love fruit.
What's your favorite fruit of them all?
Blueberries, raspberries, cantaloupe, honey melon, all sorts of things.
You truly are a passionate fruit person. Okay, Africa or Asia?
Asia.
Asia. Okay, these seem a little bit odd, but it makes sense if you, and I'll explain why. Number 7, electric guitar or classical guitar?
Classical.
Classical, okay.
I like classical music.
Great. Number 8, cranberry juice or apple juice?
Apple.
Apple. Number 9, toilet paper over the top or slung underneath?
Underneath, more useful.
Oh, okay. And finally, ice cream sundae or banana split?
Ice cream sundae.
Ice cream sundae. Okay. So, Raquel, do we have the answers that our audience has provided us?
Yes, we do. George.
Okay. Number 1, agates or tourmalines?
Tourmalines, of course.
Tourmaline. Oh, wait, we got the sound effects back. Number 2, surf or turf?
Surf.
Surf. Oh, sorry, I'm trying to get that out of the way. Excellent. Number 3, singing or dancing?
Singing.
Singing. Number 4, Android or iPhone?
iPhone.
Yoo-hoo. Number 5, vegetables or fruit?
Vegetables. Oh, sorry, fruits. I was
Fruit.
thinking, sorry, fruits. Yeah, people know you, George. Sorry.
Raquel, this is not your answer. This is the audience's answer.
George has many trees, and he's always very proud of all his oranges. I know he loves fruit.
Absolutely. Okay, number 6, Africa or Asia?
Asia.
Asia. Number 7, electric guitar or classical guitar?
Classical.
Classical. Now, this is funny because I threw this question in because this all has to do with Wisconsin now. Les Paul, who was born in Wisconsin, was in part responsible for making the electric guitar. So that was going back to your home state there. And the next three questions also reflect this. So the answer to question number 8, cranberry juice or apple juice? What did the people say?
Cranberry.
Cranberry. And George, as you may know, Wisconsin produces 60% of the nation's cranberries.
George, you are muted for some reason. Can you unmute yourself? And Brian, I cannot see you.
I think that's my fault for Brian. I think I put him, I turned his camera off. I'm sorry, Brian, you have to turn the camera back on.
Okay, I'm back on.
Eloise.
You're
I
there?
know, I arrived to make trouble here.
There, can you see me now?
Yes,
Yes.
we can see you too.
Okay, great.
And we can hear now George too. So sorry, we were
Very
on
good.
the
So we're back to normal.
cranberry. Yes, cranberry
Okay.
apple, cranberry. The next one was it?
Toilet paper, over the top or slung underneath?
Ooh, I think that was my mistake because I wrote over the. I didn't update the results. So people chose ocean versus desert.
Huh.
Sorry, I don't. That was my mistake. I
So,
didn't.
ocean versus, okay, so I'll say ocean would be underneath because there are things below it. So,
Yes, so go with
Oh,
ocean.
desert.
we're going to give that a pass on the toilet paper, going with what George selected. And another Wisconsin fun fact, Green Bay, Wisconsin is known as the toilet paper capital of the world. So
Yes.
there we go. And our final question, ice cream sundae or banana split?
Ice cream sundae.
Ice cream sundae. And our final bit of Wisconsin facts, Two Rivers, Wisconsin was where the first ice cream sundae was ever created. So that gives us 9 out of 10 questions answered correctly. Congratulations, viewers. You are the champions today. Okay. Now, let me teach you how one of you, just one of you, is going to be able to win our great prize today, which is an XRF identification of the mineral. So you're going to have to go to a website. What website? It's going to be minerals.gps.caltech.edu. Okay? And we're going to give you a puzzle, and you have to figure this out. Now, according to the Caltech website, again, minerals.gps.caltech.edu, you have to answer this question correctly. The first one who can email the correct answer to info@mineraltalkslive.com, you will be the grand winner. The question is, drum roll please, Moganite from Gran Canaria, Canary Islands in Spain is what color? According to the Caltech website there, you have to go on that website, find the answer. The first one who can properly identify the color of Moganite, you will be our grand prize winner. All right. Then do we have a little bit of time for some Q&A here?
Always have time for some Q&As.
Yes.
Excellent.
Okay, George, the first question was, is the museum open to the public? Is the exhibit open to the public?
Right now, Caltech is closed because of coronavirus, but during normal times, it's open to the public 8 to 5, except an occasional time when we have meetings inside this room.
Okay, so it's open reservation? Do you have to reserve in advance?
No, we do not.
Okay, is it free access or?
No charge whatsoever.
Oh my God, okay, great. Do you have other question for me? Hi, George, in the first place. I'm sorry everybody arrived late. So hi, George, in the first place. I'm happy to see you here. Do you have something more, other things that are not on display, like another part of the collection that would not be on display but in drawers? Or is that all that you exhibit?
No, we have 3 other major collections. The huge one is our research collection of 18,000, roughly 300 minerals, which is locked up in a different portion. It's some very, very nice samples, some just ordinary things that you don't feel bad about chewing up and doing research on. But we have almost, not quite 2,000 different mineral species in our collections for fundamental research. We have a teaching collection in our classroom that is actually quite nice compared to a lot of teaching collections. And we have what we call a working collection of things that we have no concern about people grinding up, crushing if they need quantity of materials for some experiments.
Okay, that's great. I remember having seen some great minerals within the drawers as well. So I know you have great specimens that are hidden, and
Oh, yes.
good specimens for research, good specimen for crushing and doing experiments. So that's all for the museum itself. But people were asking, I guess it was about the tourmaline, about if the color was stable or not, the irradiated color was stable or not on the pink tourmaline, I would think.
Okay. In my experience, on a human lifetime, the color is quite stable. I think it was Bill Larson told me he visited China once where he saw some of the tourmalines that were mined around 1900 that went to China. And his impression was that being exposed to room and daylight for over a century, there has been some minor fading of the color. But certainly in the short-term experiments, 10, 15 years that I have worked on, I've not noticed any significant fading. Topaz, on the other hand, not blue topaz, but sort of the brownish topaz can fade very readily. The green spodumene can fade extremely rapidly. And irradiated corundum, which is done technologically, not out of the ground, that also can fade quite rapidly.
Okay, well, thanks for clarifying that. Thanks. Still on tourmalines, I'm just reading the question out loud from Edward Zbig. Should minerals in the tourmaline group be named tourmaline or by the actual mineral name that is part of the tourmaline group?
There are like 30-some tourmaline species in the tourmaline group. For all practical purposes, you really can't easily tell which species you have without detailed, I might say expensive chemical analysis. So for practical purposes, tourmaline is perfectly adequate. If it's a pegmatite, it's probably albaite. If it's a black tourmaline, you might want to say schorl, but most of the ones I found in California have actually been phoitite. Lydicotite out of Africa is pretty well identified by the patterns. But beyond that, it's very, very difficult to just tell what they are by density or any other particular easy method, given the complexity of tourmaline.
Right, and even within the locality, it's really hard to say which one is which, because I know that we always have the temptation to go back to Mindat and to look at, you know, a locality, a mine, and look at what mine produces what tourmaline. But even with that, it's usually not enough to to be sure what tourmaline it is. I guess like some mines produce some very specific tourmalines, but not always, unfortunately. So even with that.
Yeah, well, for example, in California, like at the Stewart mine, you have dravite, you have schorl, you have phoitite, you have albaite, you have a little bit of Rossmanite. All of them occur in that one deposit.
Right. I have another question, so I'm going to read it as well from someone who didn't say his name, so I'm sorry about that. Do you measure the fluorescence spectra with UV excitation to identify activators of fluorescence? And if so, is there a database of those spectra? Because this person is actually asking, so this person is measuring some of these spectra himself or herself with some cheap home equipment.
The answer is I do it a little bit, but more commonly I collaborate with Glenn Waichunas of the Lawrence Berkeley Lab or with Michael Gaft over in Israel that are two specialists in fluorescence of minerals. Waichunas in particular uses the equipment I have here at Caltech very often for his measurements, and we collaboratively put the results out. I do not have a database on fluorescence. Certainly we have the Journal of the Fluorescent Mineral Society that has information in the Fluorescent Mineral Society itself, but no, my databases are visible color optical spectroscopy, infrared ATR spectroscopy, some Raman spectroscopy, but most of that now is in the rough database, but not fluorescence.
Okay, thanks, George. And just to add on that, I mean, fluorescence spectra, unfortunately, I never found a really good database for spectra related to fluorescence. I usually use a deuterium lamp to excite the specimens, and then an cheap ocean optic spectrometer to look at the spectra. But after that, you don't really have a good reference database, from what I know at least. And indeed, you have to look mineral by mineral and go and open books, and that's pretty much what you have to do.
Right.
Okay. Diane Caldwell-Chester. So she's asking, as a collector of minerals and a gemologist, what would the cost be for Caltech to identify minerals that she cannot identify using her personal gemological equipment? And per specimen, she's asking.
Well, I don't deal with the commercial aspect. So we do our identifications primarily for research. We aren't really a public access organization. Attard in San Diego, for example, runs an X-ray fluorescence. I believe there's a microprobe facility up in Washington that works. So there are a number of commercial people. I expect you're gonna, well, I don't want to prejudge what the cost may be, but that's not something that we're into. Sorry.
Thanks, George. I don't know, we have a lot of more questions, but maybe, I don't know, Brian, if you want to go back to the main show, and maybe we can take more questions later if we still have other people interested. It's up to you guys.
Okay. Well, we're pretty much at the end of the show here. So what I'm going to do is I'm going to do the trailer, the announcements for upcoming things, and then George, if you can hang around, and we'll see if we can get to any other questions, because I know that some people have to get back to work. So this Friday would usually be our Friday happy hour, but we're going to push it off 1 week because we'd like everyone to have a nice long weekend, just take some time off. So this Friday, we are not going to have our Friday happy hour, but our Friday happy hour is going to come back next Friday, September 11th. And what we are working on is getting some live broadcasts from a couple of the Denver shows that are going on, that will be going on that weekend. So that would be a fun kind of thing for everyone to tune into. So come on back next Friday. Check with us again on the website. Tomorrow, we will be releasing episode 10, which was our interview with Ryan Roney, the curator at the Tellus Science Museum in Georgia. That originally aired on August 5th. And that was a great interview. So check back tomorrow. It will be released then. And finally, set your calendar for next week. We've got the lads from Collector's Edge going to be joining us. We've got Steve Belling, Richard Jackson, Phil Pershawn, and even Brian Lees is going to stop off and say a little howdy. So that's next week, Collector's Edge. Same bat time, same bat channel, Wednesdays starting at 10 a.m. LA time. From all of us here at Mineral Talks Live, George, thank you so much for joining us and being our fabulous guest today. And thank you, audience, for tuning in and hanging out with us. And Eloise, I'm going to turn it back to you, and we can go through any other questions we have for George. And for those of you who have to tune out, we will see you next week. Take care. Aloha.
Okay, so I think we have more specific questions now. That's why I kept them for the end. Sarah Ritchie was asking, why did the YIG have the silver spot? I mean, she meant the, but not the reflection spots, but the silver spots. Does that make sense?
Yes, I understand. The yttrium iron garnet is grown from a melt in an iridium crucible. And some of the iridium actually evaporates and condenses on the outside of the crystal. So what you saw were little specks of the evaporating crucible adhering to the outside of the crystal. This is a problem I've seen with some synthetic sapphires, corundums, and with some of the yttrium iron or yttrium aluminum garnets. The melting point is very high. Iridium is one of the very few elements you can use to make the crucibles to heat these melts at that high temperature.
Okay, that makes sense. I guess someone was asking more about the FTIR. So the question from Maxwell Day was, how can one determine short-range ordering of atoms in minerals using FTIR? So can you just make the difference between all?
Yes. Well, let me concentrate, let's say, on feldspar. Feldspar, potassium feldspar, if the atoms are perfectly ordered, the aluminum and the silicon, it's called microcline. If they're partially ordered, it's orthoclase. And if they're disordered, it's called sanidine. When we look at the infrared spectrum of microcline, the bands are very sharp. But in sanidine, they become quite broad and they tend to merge together. So by looking at the width of the bands, you get a measure of the disorder in the feldspar and other phases as well. Same thing with the Raman spectrum. The width of the bands often is related to order disorder.
Yes, right. So you don't look directly at the ordering of the atoms, but indirectly.
Correct.
Okay. Ken is asking a very personal question, I think. Was it personally difficult to transition from bound journals, so old school, to digital journals, new school, so basically low tech to high tech? And second, were you immediately accepting all of the new technology, or did you have to pull yourself in that direction?
Well, I've been working with computers since 1964, and I've always been playing with electronics as a kid. So technology is something I find very comfortably in my environment. I don't have a problem with technology. Going to the digital version of journals, I got to admit, I kind of like to lay in bed munching on peanut butter cookies, paging through journals, finding things I would not normally read. I would read abstracts or maybe introductory paragraphs of articles I would normally pass over if I have to paw through them in the electronic media. So although electronic media is very nice, it gives me access to many more things I would otherwise have. It has a disadvantage of somewhat limiting the scope of what I normally browse just by curiosity rather than focused type of activity.
Yeah, I hear you, George. I feel the same way, basically. And more questions are coming. Just one last maybe. Carlos Torres is asking, what does a tourmaline need to be called Lydicolotites?
In one of the crystal sites, calcium has to be the dominant cation. If it's sodium dominated in the site, it's called elbaite. And if it's no cation, if the site is totally vacant, a vacancy, then it's called Rossmanite. And we judge these not by perfect end members, but a continuum, anything between, let's say, 50% sodium down to 100% sodium would be called elbaite. But once it drops below 50%, then we change the name.
Perfectly clear. Thank you very much, George. I think I got all the questions from the Q&A pretty much. So thank you so much again, George. Thanks.
Hello,
Okay.
can I, George, you have a few minutes more?
Sure. Yes.
Sorry, because I know Peter Mago was one of the earlier questions, and it's related to the Anderson. That is it related to locality, or any other Andersons could be turned red?
Well, the andesine is made by diffusion of copper at high temperature into the andesine under controlled conditions. So in principle, I would think any andesine would be susceptible to this treatment, but commercially, it seems that it's the stuff from the Inner Mongolia that hit the market back 10 years or so ago.
Okay. And then a few more. Are there measurements that you were doing, the XRF and any others, made in vacuum?
In vacuum, you have more sensitivity to the very feeble X-rays like sodium and magnesium. My particular machine does not work under vacuum, but inside an instrument like a scanning electron microscope, which is evacuated, we can actually analyze lighter elements than I can analyze in my tabletop machine. So yes, vacuum is preferable, but it's much more complicated than the simple machine I have.
I see. And the last one from Bali, what does the XRF that you analyze the zircon with cost?
Well, again, I paid for the machine. I don't charge myself to use it. Commercial sources may be anywhere from $60 to a couple $100, depending upon how much information they provide. In the academic world, we don't operate as a commercial testing laboratory, so I can't really address that aspect in terms of my own activity.
Okay, I think that's it. I just
Although there's one more question.
There's
One more
nobody.
question coming. One more question
George,
coming.
you have all day, right?
Just one more. Just one more. It's a very interesting question. Rachel Turnier is asking, why is the diamond plate used in the IR spectrometer? So I guess she's talking about the IR window used in like the diamond window. So is because diamond is transparent to the IR region of the spectrum, or is it because of its high refractive index?
Well, actually, there are three reasons. Number one, diamond has a high transparency over the wavelengths of interest. Secondly, it has a high refractive index, so light hitting the surface of the diamond from within bounces down back to the detector. That's what we have to have happen. And thirdly, diamond is so hard, the things I put on it aren't going to scratch it. Other commonly used crystals for this purpose would be germanium or silicon, but they can be damaged by hard minerals like corundum and topaz, things like that.
Perfect. That's it.
Thank you so much, George.
And for,
Oh, my
for
pleasure.
your time and sharing your knowledge and the information. We really appreciate it. Really enjoyed the show. It was fantastic. Thank you.
Thank you very much.
Bye, everyone.
Bye,
Thanks
everybody.
for joining.
Good to see you. Bye.
For
Ciao.
joining. Take care.